So chapter 23 is still EAS, but except instead of just doing a single substitution, your structure now changes. So we change at least one of the hydrogens to something else. Okay? So what that something else is going to dictate how the effect manifests in the rest of the structure. So the easiest thing to do is look for the atom that's attached, okay, that's not hydrogen, and decide, does it have more electrons than hydrogen or less? If it has more electrons than hydrogen, sometimes it's obvious because it's a lone pair. Other times it's not as obvious. For instance, if atom X was just a carbon, right, or just a methyl group, so we'll change that upper left corner. We just made that a CH3. Is atom X, that carbon, activating or deactivating?
Still activating.
Why is it still activating? I don't see a lone pair.
Yeah, but carbon has electrons that are not being pulled from those hydrogens because it still has electrons to get.
Ultimately, carbon just has more electrons than hydrogen, period. It's the easiest answer to run with. Right? So that would make it activating. What if we change the carbon a little bit and now put a carbonyl on it? It's still carbon. Should that be activating or deactivating?
Activating those.
Okay, so now the question becomes, well, what is it? Does it have more electrons than hydrogen? Well, the first thing that should jump to your mind is we have a pi bond, which means we need to look at resonance. And we look at a resonance structure, what charge builds on that carbon? A formal positive in the resonance structure. That means for that single compound, that carbon has an average charge of +0.5, because there's two structures, right? What is the charge on a hydrogen atom? 0. The charge on a hydrogen ion is +1. The charge on a hydrogen atom is 0. If that carbon is +0.5, is it more or less electrons than hydrogen? It has less electrons. Atom X in that case is a deactivator, and it's better fit to the bottom pattern. Okay? So your activators and deactivators are not necessarily blatantly obvious. There's a lone pair, or there's a positive charge. Okay? That information can be hidden. It's all relative to hydrogen, and you have to kind of watch out for that. Okay? When we go through and look at them, we clear everything off now. If atom X has more electrons than hydrogen, you're looking at it as an activator, and it is para-ortho directing. Okay? Because para and ortho are not officially IUPAC nomenclature. The para position is the 4 position with respect to our group. Okay. So if X is at position 1, 2, 3, 4. So para's at 4. The ortho is at 2 and 6. Okay? Yes, we have to count the 6. Okay? And the reason we count the 6 is sometimes it's not identical to position 2. In this case, it is identical, but we should at least be aware of it. If atom X has less electrons than a hydrogen atom, then we would refer to it as a deactivator, and then it directs to the meta position. Okay, the deactivator becomes a little bit harder because the charges build at the exact same locations as with the activator, but the charges now are, instead of being negative, they are positive. Okay? Because we don't have electron density, that's why that reaction runs slower. That's why it's known as a deactivator, because the charge build is different. Okay? In the case of the deactivator, that leaves only one position left to react, which is going to be your meta positions. Okay, so it's known as a meta director. If we wanted to refer to them numerically, it would be the 3 and 5 positions. Kind of make sense? Okay, or at least that labeling. What we just went through and mentioned and have written up here in red and in blue, that should be committed to memory. Okay? The speed with which you can answer questions with that memorized is a lot faster than having to draw out the resonance structures. So I would recommend memorization for that. Okay? Personally, I still wouldn't have memorized it. I'd just draw the resonance, but for the sake of time, memorization can work for that. Kind of make sense? Okay, you done with your picture?
Yeah.
So, structure 1. Activator, deactivator. Okay, so we have to identify atom X. Atom X in this case is that carbon. Carbon has more electrons than a hydrogen atom, so that is now an activator. So this would be an activated reaction. What does that mean about where the substituent should go? I now have an activated ring. It should go to the para or ortho positions, which means the answer I would get would be having the ring, there's my methyl, and at the para position, what do I expect to see? This piece. Okay?
Does it depend on the reagent if it's a para or?
It doesn't. So define reagent, and so to help with that, I'll make 2 boxes. Red box, blue box. Which reagent are you referencing? No. The blue box has nothing to do with where it is located. It is only the red box. Okay? When we're talking about where the substituent goes on the ring, it has to do with that atom, atom X. Once the thing has been added to the ring, now we potentially have a problem, because if I was to say try and run the reaction again with the green box, I have 2 substituents. Where should my next reaction occur? Ortho's not a bad statement. The problem with ortho is ortho to what? The methyl or the acetyl?
Isn't that acetyl deactivating for that?
The acetyl is deactivating, yes.
Shouldn't, whenever we get the netted to that?
So there's a reference that we could try and walk through on this. Okay, there's a suggestion that because that is a deactivating group, it should direct to the meta position to that group. Everybody understand that statement and understand that arrow?
But then again, it should be.
Wait,
carrot to
wait,
methyl.
wait. Does everybody understand that statement? To the deactivating group, that acetyl group, that carbon at the bottom, our next substitution should happen meta to it. So what we're saying is that green atom is a deactivator because it has less electrons than carbon, which means it should go to the meta position. The meta position is always in reference to a group, not a number. Right? So we would go meta to that. So we're starting our counting in that case at the bottom. 1, 2, 3. There's our meta position. Everybody understand all of that? Okay, you're making a face pretty. What's your face? Yeah. What's your question about that statement?
So I get that it's para and it's ortho initially, but is it because it's not stable enough?
Nope. This is your product of step 1. That's it. So what we're saying, step 2, do something else.
But there's no step 2 written on.
There is no step 2 written on there, and we can fix that confusion really quickly. Step 2. Iron tribromide and Br2. That reagent is going to do what? Act as an electrophile. Yes, the end result is add a bromine. Okay. Add is really a bad word because we aren't adding bromine to the structure. We're doing a substitution. So I would argue the substitution or doing a sub of bromine makes more sense. So we're saying we now run a second reaction. The question now becomes is where should that bromine go? in this second reaction, the suggestion was made that the new group that we just added is a deactivating group, which makes it meta-directing, which means I should place the bromine at that location.
Could do either sides too.
It could go to either side. Does anybody want to challenge the information that has been put out at face value?
So the bromine goes at that carbon or next to it?
So if we were to draw out that product, what we are suggesting is that the bromine should go there.
In a step two like that, don't you have to run the reaction and see what happens because you have that methyl group as well?
Okay.
That's opposing substituents.
Second statement, so we got two statements in there. One, don't we have to run that reaction to see what happens? We always have to run the reaction to see what happens. If that was all we could do, we wouldn't be in the lecture class. You're required to pick up some of that knowledge to be able to say, this is what I would expect to happen when we move into lab. That's what you're told to memorize and work with. Okay, so that's the first statement. The next statement you made is talking about the methyl group. And I completely agree, we need to talk about the methyl group. That's another statement, another question that we haven't addressed. The question still stands. The acetyl directing to the meta position. Okay? All I'm asking is based off of that as our atom X, should bromine go there? That's it. That's all I've asked.
No, I don't think so.
Okay? Why should it not go there?
I read from the book that if you have like two different opposing groups.
Stop. No. All we said is we assumed the acetyl,
Yep.
bottom group, where should the bromine go?
Yeah,
Right there.
to the acetyl.
To the meta position. That's it.
Period.
We have not evaluated the methyl group, so don't evaluate it. You have to separate these things as two separate thoughts. If you don't separate them as two separate thoughts, what happens?
You mess up.
You mess up. You start to confuse them with each other. Right? So what we need to do is just address, are you happy with that statement and that statement alone?
Yeah.
Yes. Okay. Methyl group. Where do you expect the methyl group to direct? Okay. The methyl group is an activating group because atom X has more electrons than hydrogen, so it would direct where?
Para/ortho.
Para/ortho. Why are you choosing to ignore the para statement?
Because there's something there and it can't go there.
EAS does a substitution for what? Hydrogen. Is there a hydrogen at the para position? No, so you can't do substitution at the para position because there is no hydrogen there, period. Okay. If you can't do substitution at the para, we would now have to evaluate, does that direct to any other location? Ortho. Where's the ortho position? Where is the ortho position to the methyl group?
2,6.
2,6.
Okay, our 2,6. Where's the 2 position?
Meta to
Where the bromine is located. Okay, or the opposite. By that same token, the other one could have gone to the opposite too, so we'll ignore that as a statement. So in this case, the methyl group says put the bromine there. The acetyl group says put the bromine there. Where should the bromine go? That spot. Okay. Does anybody see a potential issue that could arise further on down the road? What if one group directed in one position, the other group directs to the other? There's now conflicting evidence between those two. Which one wins? The activator is the one that wins. Okay? So the argument that was made about this green directing from the acetyl group is actually completely irrelevant. We only care about the activator. Because the acetyl is a deactivator, I'm concerned about the methyl direction. The methyl is going to place the bromine there. I don't have to worry at all about the acetyl group. Kind of makes sense? Yes? Could you have more than 2 groups? When we started this whole thing off, how many groups did we have? 0. When we moved to today, what happened? We added 1, then we added 2. Could we add a third? Yeah. Could we add a fourth? Yeah. All of those are potential options. Okay? We're going to have to be very careful about those because each of those are their own reaction, and each of those substitutions is potentially going to change where the next substitution can happen. Which means the order in which you do your substitutions is very important. Okay, so you have to be able to track the directing effects of each of those groups as you move through.
So if you have added or substituted an activator there, and it wants ortho, but does the methyl take priority since those first, or is it the most recent one? You know what I mean?
I do understand what you're saying. It is the strongest activator, period. So it is always going to go based off of your activator, and it's always going to be the strongest activator that directs. So 1, 2.
Yeah, follow up to Mo's question. I mean, in essence, you're gonna get the para or ortho products, but as far as the para ortho avoider or the meta, product, right? Para ortho avoider, otherwise known as the meta product.
Okay.
You're still gonna get it in small percentages. It's still gonna get reduced.
So
Like
talking about side
5%.
reactions, and you're fine to address side reactions, you never get tested on that. What you're concerned about is the primary product.
I mean, with that acetyl group, like, you're still gonna get some bromine going there that was forced by the acetyl, right?
There's no way you would be able to tell the difference.
Okay, let's say it was something else, and you were able to tell me.
You wouldn't be able to tell the difference because they're both directing to the same position. Because they're both directing to the same position, there's no way you'd be able to evaluate which one directed better than the other, beyond our statement that this is a deactivator, and we have learned that if that group is present, the rate of the reaction slows.
Could you tell the difference if you radio tagged it?
No. Because again, nothing is different about where that position has shown up. There's nothing to radio tag.
So how do you use a cardio charge?
Oh.
Do you use that to determine which activator is the strongest?
Deciding which activator is the strongest, you should be using the same rules that we've been using the entire semester. An acronym that is potentially used is cardio. If you know all the terms behind it, that's okay. The issue with it is it doesn't nuance some of the differences.
You're saying order of the substitution matters, so for like the first step, how would we decide between para and ortho? Because when that affects
So in our substitution, how would you get asked in a way that it would be the substitution matters? The order matters. Yeah, there has to be multiple steps.
Can you elaborate on that question?
How would we phrase a question to make sure that the order in which you ran the reaction was important? Because I believe that's what you're asking.
Can you force one position over the other if you put something there first?
How would I ask that, though? How would I ask a question where the order mattered?
If you gave us a product and you want us to find the reactants?
If I asked you for the product and said, what reactants are going to get me there, that's when the order matters. If we're running in this direction, does the order matter? You don't even know where we're going. We're just doing it. Right? We're just saying, hey, we're doing this, we're doing this, we're doing this. The order doesn't matter. Why? We just said we're doing it. We don't have a goal in mind. Only when you have a goal in mind does the order matter. Yes?
Why did we choose para first instead of ortho first, if it's para or?
Good question. I can still erase everything. So why did we choose para over ortho? Why is the para more stable than the ortho? It's only a deactivator in this reaction, so that has nothing to do with it.
Steric hindrance.
It's a steric hindrance argument, that's it. So when we're looking at EAS, it's electronic effects first, steric hindrance effects second.
If it was smaller, we could have gone with.
You should always go with para first. Para will dominate. The question is how much it dominates. Okay? On a multiple choice test, it dominates entirely. Okay? With groups, these aren't that large. You're probably 70-30 as a guess. Okay? Which gets to one of Cass's suggestions about, well, couldn't you get this other one in a smaller yield? Yes, I don't care. Focus on the larger contributor. 2. We're actually going to look at 2 answers for 2. Whoops, should not have erased the reagents. But I wanted more space, so we're going over this way. What would you predict? So what is atom X? Nitrogen. Does nitrogen have more or less electrons than hydrogen? More, which means? Activator, which means? Para or ortho, where would we expect to see our group? Para position, what's our group? NO2. All right. Turn, go ahead.
Sorry. So you just assessed if it's para based off what the attached group was on the benzene?
Yep, exactly like we said off those resonance slides. It's exactly what you have to do. That's what dictates it all. It's phenomenally nice for that reason.
Knowing that that what is actually being substituted is NO2, that just memorizing when you have H2SO4 and HO2.
Knowing that the product needs to have NO2 on it, yes, that goes back to knowing what that reagent does, that reagent sequence, and yes, that's exactly it. You have to have it memorized. That's the easiest approach, is just memorizing that reagent. What if I told you that there is a suspiciously large concentration of this as a product? I'm not saying this is the product, but I'm saying there is a suspiciously large concentration of that species floating around.
There is no catalyst.
Then,
So we can, a couple options. One, you can call, I just learned this one, allegedly.
what's that?
Bullshit.
Huh?
Bullshit.
See that?
Yeah, right, see, it's the bowl.
That's good.
Yeah, no, that's good. Thank you, Internet. So you could call that.
The nitrogen had the NH2 had originally been protonated to NH.
Why would the NH2 get protonated? Why are you suggesting that?
Because you have a product at the meta position.
For the product to go to the meta position, what had to happen? It had to be a deactivator, which means the atom connected to the ring must not have electrons. Nitrogen clearly has lone pair electrons, so what has to happen? We have to remove those lone pair electrons from being able to donate into the ring. So where do we put them? Whoops. We put them with a bond to hydrogen. It says NH2. Oh, yeah, it does. So that it is now positive. Once it is positive, now what happens? Now it would go to the meta position. Everybody see that?
It's only because positive?
It is only because that atom is now positively charged. And officially, it's because that atom has less electrons than hydrogen, because it is positively charged. Would I expect that nitrogen to get protonated? What are you suggesting? Nitrogens are usually basic. Are we in an acidic enough environment to protonate that? We're in an acidic enough environment that sulfuric acid is doing what to nitric acid? Protonating it. We're in an environment that is so acidic that nitric acid, a strong acid, acts as a base. This is an insanely acidic environment. Okay? So we might expect a higher than normal concentration of the meta product for that alone. Kind of makes sense? So one of the things you might need to worry about is secondary reactions coming in and preventing one reaction from happening or changing how you would expect it to react. Okay? You all, or not you all, 3 groups did an experiment. Okay? Acetic acid with aniline and Br2. Where did the bromine go in that reaction? There were 4 people that did that. We do have some absences, but I'm pretty sure not all 4 people are absent. Who reacted aniline? Yeah, and that's where people raise their hand and are like, damn, I don't really want to do that. Okay. What did you get as a product? You got notes? Pull them up. Okay. And for the rest of you in lab being like, I'm glad that's not mine, guess what you also have to do in your lab report? Talk about the results of that experiment. So everybody's supposed to have these results. Aniline was 246, meaning where did it direct? The ortho and para positions. Right? So acetic acid is not a strong enough acid to protonate the amine. Nitric acid, sulfuric acid becomes kind of questionable. At very least, that reaction is going to be very, very slow. Right? Make sense? 3. What do you expect to get for 3? So I heard a suggestion for the ortho position. Does anybody want to support that? As a hint, ooh, we see a hand too. What do you got?
I don't know, it's a stupid question, but can you use resonance to get it to where that positive goes away and then you get para?
It's an interesting idea. How would we do resonance to get that positive to go away? What do you want to do?
I don't mind, that breaks out to
Okay. With the negative, you could bring electrons in. You'd exceed the octet, so you could kick electrons out. The end result is you still have a nitrogen with a positive charge. Okay. But you're saying that nitrogen has a positive charge, which would direct where?
meta.
Where was the bromine placed in our first suggestion? That's in the ortho. Should the bromine go to the ortho position if the nitro is a meta director? No. Where should the bromine go? Okay. It should go to our 3 position. One of the things that will be confusing is rotating that structure. Ortho, meta, para, all of the numbering all go from a primary substituent. It's not the top atom being number 1. Make sense? Okay, so I agree. This one should be brominated in that position. Good job. What does brominated mean? You added bromine. What did we do? Okay. Number 4. What do you expect for number 4? What's that? Okay. The reference again is jumping to the answer. Our carbon is electron withdrawing because we have a resonance effect with the oxygen pulling electrons away, which means we have a large partial positive, which means atom X has less electrons than hydrogen, which means we have a deactivator, which means we will direct to the meta position. I was trying to understand why you were flashing 3 upside down. I was like, yes, it is 3, but why is that upside down? And we would place our CH3 on the structure. Does everybody agree? Anybody want to dissent and say, no, that is not true? Because unfortunately, that is the wrong answer. I know. It was done unintentionally. Which of the reactions is not expected to produce products? This reaction should not produce products. Why?
Because that's CH3Cl.
Yes, CH3Cl in the aluminum trichloride is known as a...
Toxin.
Probably. Friedel-Crafts alkylation, and our Friedel-Crafts alkylations require activated rings. Is that ring activated? No, it's actually deactivated, which means that reaction won't happen. So it was one of the complications that we talked about last week with the Friedel-Crafts alkylations. They don't work with deactivated rings. Okay? One of the big drivers for that, can you form a primary carbocation? No. That's why you need an activated ring, because we really need a strong nucleophile to react with that as soon as it forms. The lifetime of that carbocation is so low that we never get the nucleophile to react. So we end up getting no reaction. Okay, so you have to watch out with that with the Friedel-Crafts alkylations. Okay? Have to have an active nucleophile. The acylation, on the other hand, is okay. We don't need an active nucleophile. Why do we not need an active nucleophile? What is different about the carbocation formed in the alkylation versus the acylation? What is special about the acylium ion? We have resonance stabilization of the carbocation. It is that resonance that allows it to form such that we don't need an active nucleophile. We can run it with a deactivated nucleophile. Okay? That's your big difference between those two mechanisms. Interestingly enough, this kind of question is a super common question on the ACS. Which of those two Lewis structures is the correct Lewis structure? Or the most correct, we should say. The triple bond one is the most correct because everything has its octet. Okay, so you got to watch out for that. Okay. Aromatic amines. While we have the NH2, we said that that could act as a base and pick up hydrogens, say, from a nitric acid. Okay. If we look at our Friedel-Crafts reactions, we add a Lewis acid catalyst, the aluminum trichloride. It turns out the aluminum trichloride as a Lewis acid is pretty phenomenal with the Lewis base of the nitrogen. Meaning if I try to run a Friedel-Crafts alkylation on a structure that has a nitrogen in it, what happens?
No reaction.
We convert the activating nitrogen group into a deactivating cation. The instant is deactivating. What happens to the reaction? We kill the reaction. Okay, so the nitrogen can be very tricky. We have to deal with it when it comes to the Friedel-Crafts reactions because of that Lewis acid catalyst, the aluminum trichloride. Okay. So, what do you think here? What should our product be? What is atom X? Oxygen. Does that oxygen have more electrons than? It's an activator, which means it directs. Does our para position have hydrogens?
Yeah.
Yep, so that's where we should run our first reaction. What do I want to place there? I will place the CH3 coming from the reagent mix in the middle. Yeah? What can you tell me about this product? Easier question. What can you tell me about that product in comparison to your starting material?
That's more nucleophilic.
Why is the product more nucleophilic?
It's added more electrons to carbon and metal.
We added a new atom X. What is that new atom X?
Also donating,
It has more electrons, which means
it's donating into the ring.
it's donating into the ring, which means the ring is now
More
more nucleophilic. If it becomes more nucleophilic, what happens?
explodes.
Not quite. It reacts again. So remember, we're running these at huge concentrations or huge amounts. The very first reaction that runs, we get now some product. If the product is more active than our starting material, what does the product do? It reacts with the reagents instead, which means I'd run the reaction again to put another methyl group on. We run into the exact case that we were talking about before, because we now have two directing groups. The oxygen directs now to the para positions. Where does our methyl direct? Sorry, ortho positions. Where does the carbon direct? Two ortho positions as well. Which ortho? It's ortho. Where is the methyl's ortho? Okay. Our ortho and meta positions are only in reference to your substituent. Okay. This is why numbering becomes a better system. Our carbon is going to direct to the ortho position of it, which is now there. What becomes the problem? Which one of those positions is likely to do the first substitution?
The strongest one.
The strongest one, the strongest activator, is going to force the most electrons, making the strongest nucleophile, which means our next substitution is going to go ortho to the oxygen. We'll put the CH3 there. What can you tell me about this product? It is even more nucleophilic, which means it goes again. Okay? This is a massive issue with our Friedel-Crafts alkylations. Okay? It is very common to get polysubstitutions, multiple substitutions, because every time you put a methyl group on the ring, what happens? It becomes even more reactive and more likely to continue the reaction.
Is there a way to stop it?
So is there a way to stop it? Sort of. Okay? So we're going to do a couple things as a sort of here. Number one, we're going to switch the reagent from being CH3CHL to CH3CH2Cl. Okay, for those of you going, well, that doesn't seem like much of a difference. Good. It isn't much of a difference. If we ran the Friedel-Crafts alkylation, we would fully expect to see the poly substitution. Okay? I don't want to do a poly substitution. I just want to do a single substitution. How can I get, no hints included, to just the para substitution? Change the reagent. Which reagent?
The one in the blue box. And the second one with the arrow.
The second one? This one here? What do you want to put there?
Wait, no, there. Top one.
Oh, this one here.
Yeah.
Okay, what do you want to put there? What do you want to do as your reagent? I think that's a good idea. It's usually a good place to start. How have we had any carbon electrophiles in all of our reagent lists? Could we put a deactivating group? So remember, and as far as just shouting out different answers, remember, we're reacting with a benzene ring, which means we're not just looking for any carbon electrophile. We are looking very specifically for a carbon electrophile that reacts with aromatic rings, which means we should be using our reagent list. And in that reagent list that we've talked about, there are two carbon sources. One is the Friedel-Crafts alkylation. The other is the acylation. What would the result be of that reaction? But I don't want a carbonyl. How would I get rid of the carbonyl? I could add H2 and palladium. Okay. That's going to reduce away the carbonyl. So if we're trying to put carbons onto the ring structure or in an EAS type reaction, we very commonly go through a Friedel-Crafts alkylate or acylation. Why is that first product less likely to do polysubstitution? The group I just added is a deactivator. That deactivates the product from reacting more. My reaction is going to continue to react with the initial reactant. I don't have to worry about it doing polysubstitution. Once I've got that product, I then need to get rid of the carbonyl. How could I do that? I can just do a reduction. Make sense?
I'd use the ethyl chloride up there. Just because, what were you trying to show there instead of the methyl chloride before?
How many carbons did we add?
Those are the same stuff that we had.
Sort of. How many carbons did I add?
You added
2. If I tried to make this a methyl chloride, what becomes the problem for adding 1 carbon?
I'm just saying, like, the ethyl chloride was the same.
Was a
substitution, right?
Yeah.
Yeah.
So why did I switch it to ethyl chloride as opposed to methyl chloride? What would our reagent be? What would our reagent be if it was a methyl chloride? I need 1 carbon. How many of you like the look of that structure? Ta-da! There's the word. Okay. By simplifying it out and getting rid of that weird-looking structure, we can now see the 2 carbons go on. That's it. Okay? So there's our polysubstitution. Okay? The ethyllium works really well. Okay? That minimizes the polysubstitution. Yeah.
How is this ring activated? The other ring wasn't activated, that there was no reaction, and that this is.
So why is this ring activated? We look at atom X. Atom X has lone pair electrons, which makes this an activated ring.
How does methyl, I know you mentioned this earlier, but how does methyl?
We'll deal with methyl in a second. If it seems like I'm forgetting, just let me know. Is this ring activated or deactivated? Touché. Is it an activated ring or a deactivated ring? How many of you want to say this ring or this new structure is now activated or deactivated? How many of you want to say it's activated? Okay, why is it activated?
The activator is stronger than the deactivator.
We have 2 substituents, so we look at each of those 2 substituents independent of each other. We have oxygen versus carbon with an electron withdrawing group. So we have a deactivator at the bottom, we have an activator at top. Which one dominates the reactivity of the structure? The activator. So this ring is activated. So what you said initially was, why was that ring deactivated? Sort of. This ring structure is absolutely still activated. But what are we concerned about? I'm not concerned about just this structure. I'm concerned about that structure relative to the structure that made it. I'm comparing these 2. Which one is the stronger activated ring? Top or bottom? Top. Why? It only has the activator, whereas the bottom one has a deactivator. That structure is still absolutely activated, but it is not as activated as the top structure, which is why our reaction stops after a single substitution. Okay? Or at least we minimize polysubstitution, which is kind of an important word here, but for all intents and purposes, we stopped it. Okay? So we get minimal polysubstitution. Okay? So here's a fun one. What if I put a halogen up there? What if atom X is a halogen? What do you think? Activator or deactivator? Definitely activator. Why is it an activator? Has lone pairs. So if I had, let's draw an example structure. Let's try to not give anything away. So we'll pick a nice neutral color here. put a bromine, is this structure activated or deactivated? So Preeti's saying it is activated. Why are you saying it's activated? Atom X, the bromine, has more electrons than hydrogen, which means activated. Okay. What are you saying, Mo? Because it sounds like you're calling Preeti out.
Yeah, I am. It's deactivated because you can't donate them in. Bromine chemical bond.
Halogen's not going to share electrons in because they could only form one bond. They're so electronegative and they can only form one bond. He's saying they're deactivators. Okay? So who's right? Oh, Preeti's ceding already. Preeti's saying it's Mo's right. You're both right.
So we can have two different products, is that what you're saying?
The halogen is not willing to share electrons, so it does deactivate the ring. But because it has electrons, it directs to the para and ortho positions. That was supposed to be red. So your halogens are tricky. They go both directions. They split the difference. Okay? They are less willing to share their electrons than the hydrogen, but because they have those electrons, they can direct the substitution to happen at the para and ortho positions. There are advanced explanations that can go into that. You don't want to see it, just deal with it. Okay? So I would argue when it comes to EAS, you have to have your reagents memorized and then 3 ways to look at activating and deactivating. Activator, deactivator, and then halogens. Okay? Of all of the chemistries we've looked at this semester, these are by far the simplest. Okay? You just have to have those pieces memorized. Okay? Or you deal with resonance. Those are your 2 options. By now you should be pretty solid at resonance. If not, here's your opportunity to shine with your memory. Okay? So, multiple X or substituents. Let's take a look at the first one. Where do you expect the bromination to occur? Okay, so we have the methyl group. Where does the methyl direct? Okay. Para or ortho. Why are you choosing to ignore the nitro? The nitro is a deactivator. This is commonly done on the test where they write it out as NO2. Why do they write it out as NO2? It's very hard to see that that nitrogen actually carries a positive charge. Okay? And as such is a deactivator, which means the methyl group's going to dictate where the substitution is going to happen. Where is it going to place it? Okay. The para is the most likely position. Okay. What would the next most likely position be? Why the left ortho? The deactivator doesn't make that more reactive. Say that again, Marcus. Position 3 is sterically hindered. You get 2 groups button up against it.
Why are you labeling it 2, 3, that way?
Where's the first substitution happen? Where's the second substitution happen? Where's the third substitution happen?
Okay, so you're numbering it like that. You're not numbering it like the ring. Like you do.
No.
Okay, thank you.
Okay, that's numbering according to substitution patterns. What about the bottom one? What's that? This becomes tricky. Why? They're both activators. So the oxygen would direct para-ortho. We really only have the ortho positions. The methyl, also an activator, directs para-ortho. Which substitution wins?
I want to say it's meta because you have nitric acid.
Meta doesn't mean anything because you have to put a reference down to it. If there's only one substituent, I can accept meta. And your vagueness in that statement becomes okay because there's only one place. Because there's two substituents, meta can be virtually anywhere.
Because it's like that nitrogen.
Okay. When the nitro group is attached, where does it direct? Meta. Is the nitro group attached? No. So I don't care where the nitro group directs because it's not on the structure. Remember, our direction only happens from the aromatic ring. Where should I place the nitro? Ortho to the oxygen because oxygen's a stronger activator than the carbon. Okay? So the nitro substitution should happen out here. Make sense? Okay. Activator trumps deactivator, stronger activators trump weaker deactivators. Where do we expect the substitution for the first one? Which one's the stronger activator? Carbon or carbon? Well, you have to compare what's attached to the carbons if they can actually do a resonance effect to greatly affect the electronic environment. Unfortunately, no. As Marcus suggested earlier and Mari's suggesting now, what's the issue? We're going to have to worry about steric hindrance. Steric hindrance is going to drive a lot of this. So we're talking about either placing the nitro group ortho to one or ortho to the other. The red one is sterically hindered because of that methyl group, which would suggest we would prefer the nitro to go closer to the least sterically hindered one. So the electronic effect comes first. We don't have a significant electronic effect, so then we evaluate sterics. Okay. Kind of like how we evaluate where electrons are located, resonance, versus molecular effects, induction. Okay. How about the bottom one? Where do you expect the nitro to go? Whoops.
Can you go para to that red one? And avoid all steric hindrance? I mean, it'd be like the same thing up there.
Say that again?
It'd be like the same thing up there, right?
Oh, and I forgot that one.
If you went para to the red one?
So we've got both of those directing to the ultimately the same three positions. But now the question becomes is which of those positions is more active? Okay? Hopefully everybody sees the top one has the most steric hindrance, correct? You get a steric effect from the methyl and from the isopropyl. Something going on with my coloring? Oh, there it is. Okay. The lower left hand, you get a steric effect from the isopropyl. The lower right hand, we get a steric effect from the methyl. So none of these is perfect. Which of them is the least imperfect?
That one?
The lower right hand corner, we would expect the nitro to do a substitution. At best yields to that lower left hand corner. That's my right hand corner for those of you curious about left and right. And we would expect that for a product. Okay. Are these going to be a mess as far as yields? Yes. Right. But what they're really trying to push at with these kind of questions is what's the difference? Do you recognize electronic effects? Do you recognize steric effects? Make sense? Okay. Anybody see any problems with trying to do this synthesis? What did you do, beginning to end? Substitution. Okay, what kind of substitution? SN1 or SN2? Trick question. Come on. What kind of substitution? EAS. It's not SN1 or SN2. Okay? In that substitution, what did you substitute? Okay, a hydrogen for a bromine. How do you do bromine via EAS? Br2 and FeBr3. FeBr3 is your catalyst. So when thinking about reagents, your reagent focus should be on the bromine, the Br2. Right? What would be the problem of running this reaction? Right? There's steric hindrance, and if we just ran this outright, where would it go? If we just ignored steric hindrance, it's primarily going to go to the para position anyway. And yet, where is it? It's at the ortho. How do we prevent the para substitution from happening? Change it. Put something there that prevents the bromination from happening. What could we put there? Pineapple is not a bad suggestion. Any substitution with that starting material, though, will go para. So the question now is, what is that something that we put on there? Okay, if we work with the pineapple,
Yeah, because pineapples are deactivators. You haven't drawn one in so long, they're so good.
that one was not one of my best ones. We would then run the bromination. And then what do we want to have happen?
Remove the pineapple.
Pineapple's still on there. Then we need to be able to remove it. So the whole point of the pineapple is to show something needs to go on and something needs to come off. It's acting as a protecting group. Which of my reagents would allow me to do that? There's no way that we've talked about yet to get an oxygen attached to the ring. How would you remove the methyl from the ring? So it's fine to put something on, but we also have to think about the removal process.
What if you take a strong base to remove the hydrogen from it?
It won't be strong enough, unfortunately, and even if you did, now you have an even stronger base with a negative carbon.
Put some sort of nitrogen thing on there, or is it down nitrogen gas?
So we could put some kind of nitrogen thing on there, like say go with the nitronium, which by the way, this is not my favorite way of doing this, just for the record, because it's going to be painful. And then we could reduce that down. All right, and then we'd have the amine. What could we do with the amine? And at some point in here, we would do the bromination. I'm not even worried about that yet. What could I do with the amine? Cass's favorite reaction. And I actually don't even know the next one. Yeah, I don't remember the reagent for this. I just know you can do it. Scheiße. Maybe H2. Check. It's in the PowerPoint, yeah. It's on the CuBr is going to put a bromine on and where the nitrogen is. I'm not trying to put the nitrogen on. What am I trying to put on? I'm trying to put the hydrogen on. That's what I was thinking, but I thought that was for the fluorine.
Well, it has to be a negative hydrogen, right? 'Cause it has to kick off the negative.
Yeah, the phosphorus does some oxidation chemistry. Do you have it pulled up? No, Sandmeyer. You need to go lower. far right. Oh, just for the record, just looking at the slides, H2PO2.
Oh, you were one off.
I was one off. That was pretty cool.
H3.
Okay. H2PO2. It does say H3?
Yeah.
Oh, didn't I write H3?
No, you did it H2PO2.
I'm going to have to go back and check the video later. I thought I had that. That would put the hydrogen on there. Okay. That doesn't get us our bromine, but what that does is provide us the protecting group. Okay. So where should we do the bromination in this sequence? If we did the bromination first, what happens?
Go to the para.
Bromine goes to the wrong spot. What if I did the bromine second? That'd be fine. The carbon is a directing group, ortho-para. It's going to direct there. I'd put the bromine on. What if I did it as the third step? Two activating groups. The nitrogen would be our director now. The bromine would go here, not where I wanted it. Okay. So the location of when we do the bromination is really, really, really important. Make sense? So that's cool. We could do Cass's favorite reaction with the Sandmeyer fun stuff. You're welcome. I saw the little bite on the lip there, kind of the following. That's all you were saying, following. All right. How else could we do it? Was there a reversible reaction? Give you a hint. Yes, there was. There was exactly one reversible, easily reversible, because I would argue that Sandmeyer one was a bit of a beast. H2SO4 concentrated instead of a pineapple. I'll put on the sulfate. Whoops. The sulfate is deactivating, so it's not going to affect the substitution. How do I get rid of the pineapple? Exactly right. We use the exact same reagents, sulfuric acid, except this time not concentrated. I would use dilute. Okay. So, two ways we could go through and approach that reaction. That's going to get us the best yield. Okay? Exciting stuff. Okay, so we needed our blocking group or our protecting group. Okay. The other thing we do is look at this sequence. Let's break this one down because I think this is probably kind of important. What reagents do we use to get bromine on? Br2. What reagents do we use to get the nitro on? HNO3. What reagents do we use to get that group on? Our acyl chloride. 1, 2, 3. 1, 2, 3. Where does the bromine direct? Whoops. Para and ortho. Where does the acyl group direct? Meta. Where's the nitro direct? Meta. Which order do I run these three reactions, starting with benzene? So the suggestion is first to do the bromination. Okay, this one, it literally doesn't matter where we place it, so we could just put the bromine, well, let's put the bromine on where we want it. Where do we want it? Oh, let's not rotate the structure. So we put our bromine on. Then the suggestion was, okay, the acyl chloride. And then HNO3. Technically our HNO3 is with sulfuric acid, and our acyl chloride is with aluminum trichloride. Could we have exchanged the order of the last two, green for blue? No, why not? Okay, then the nitro would have added to the para position. Fair enough. There's another reason why we can't do that one. What does the nitro do to the ring? Deactivates the ring, which is going to prevent the acyl chloride reaction. Technically, our bromine was actually deactivating. I'm not even sure this step would actually work. Okay. So we might have to do all sorts of other fancy, tricky chemistry to deal with it. Okay. But recognizing that patterning through it, that's the ultimate thing that you need to get when we're talking about EAS reactions. They really push for those type of synthesis. Do you recognize the pattern in which to move those? How are you guys doing with EAS? You done with it? Want to be happy with it? Move on to something easier? Yeah, easier is an understatement because I don't think this is easier. We can actually reduce the aromatic ring. Just like alkynes, we could take sodium metal and ammonia and we could reduce it down to the alkene. Okay? That reaction was extra special. Why was that extra blah, 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 blah. Why was that particular reaction special? It produced the trans alkene. Okay? Most of our reductions performed cis addition or syn additions. Okay? When we're looking at the sodium metal and ammonia, it actually gives you the anti-addition. Fun thing about sodium metal is it is so reactive that it will force benzene, an unreactive species, to react, and it will reduce the benzene. Okay? This is known as the Birch reduction. Okay? And notice with this, we have just a normal benzene. Do we always have normal benzenes? No, I agree. We usually throw a substituent on them. Is that substituent going to affect where the double bonds show up? Okay, would it matter? So if we did that versus that, are those chemistries different? Yes. And because those chemistries are different, what does that mean? Just like with EAS, we have to evaluate the directing effects of that X group. To really decide how that works, you have to be aware of the mechanism behind it. The mechanism, just like it was for the triple bond, is a nasty radical anion mechanism, which is all sorts of fun and excitement. Okay? The most important part in that mechanism is the anion. Because when we shift through to the aromatic ring, our active species is that negative charge. That's what's coming out to pick up the hydrogen. Okay? So what might we want to do with our atom X? Because there is one option where atom X is located here versus atom X located here. What might you expect? Go ahead.
I was going to say with the electrons as well?
Yep. So we either run the reaction where atom X is on the carbon with electrons, or we run the reaction where atom X is on the carbon without electrons. Not quite sure I follow. If atom X is a nitro, is that where I want it to be? Okay, I didn't ask deactivating or activating. If atom X was a nitro, positive charge, do I want atom X to be the red one or the blue one? Why do I want it to be blue? There would be resonance to stabilize it. The negative charge would be stabilized by that nitro. See that? Okay, so that would suggest pretty unfortunately you were wrong, but before we freak out too much, atom X is an oxygen. Let's not make it a base. Now, which of my answers? Do I want red or blue? Why red? A negative charge next to a negative charge, that would be bad. So half the time, Preeti, you were right. I want the red one. The other half the time, you're wrong, and we want the blue one. What changed? It affects electron donating versus electron withdrawing effects. Okay? So what we're looking at is noticing that the negative charge is forming, okay, at what will be the sp3 atom. Okay? If I have an electron withdrawing group, that's where I want the double bonds to be on opposite sides. If I have an electron donating group, I want it to be attached to the carbon with the double bonds. Okay? So you can go through and do kind of resonance effects behind that to kind of manipulate that. So if we look at the donating group R, right, I do not want a negative charge building on that carbon, which means don't reduce that position. Okay? Which means when I draw that product, R group, double bond. Where should the other double bond be? Directly across from it. Okay? What happens if I move to an electron withdrawing group? That carbon is positive. What charge do I want building next to it? I want a negative. Which means that needs to be the site of the reduction, which means no double bond connected to either of those two carbons. Which means the double bond needs to be. Okay? So knowing something about the mechanism and those donating and withdrawing effects can help you predict those products. If you don't have that knowledge, you just have to memorize the results. That's why I tried to just drop them on there so that you could try and see those end results. Okay? So if it's a donating group, we want it placed where it is not reduced. If it's a withdrawing group, we want it to be reduced. Okay? And because I don't think that was bad enough, what's happening in that top reaction? Substitution. What's with the face? It's just substitution. How bad could it be? What's that? Leaving bromine. Isn't that normal? We've never done it on a ring. And in fact, if we looked at this as a standard substitution reaction, SN1, SN2, we would say it doesn't happen. Okay? So what someone went through and did was probably trying to react the base with some other functional group in the structure, and they got this weird result. Okay? They had to go back and explain why they got that weird result. So number one, NaOH, decently strong base, fairly high heat. Okay? The next big thing that's on this is if we take a look at that reaction, it's only really happening if there's a nitro. If I go through and try those same conditions with bromine, NaOH followed by our H3O plus as our second step, we get no reaction. So the nitro is doing something here. What is that nitro doing? What do nitros do? Deactivate by doing what? Withdrawing electrons. If these electrons shift out, what charge starts to build? Positive charge. Does that carbon want to be positive? No. So what happens? It starts to seek out electrons from the hydroxide. Okay? So we have to have that strong withdrawing group. Somebody else started playing around with this just to see what would happen, and they switched up to a different species instead of hydroxide. They switched to a slightly weaker nucleophile, stronger nucleophile, sorry, with our NH2 to see what was going on. Okay? This time they also changed it. Instead of it being a nitro, they made it a methyl. And when they ran through the reaction, they got the same thing. They did the substitution. Cool, there it is. And that. They got two products. That seems really weird. Can we get two products like this on a substitution, different locations? Most substitutions, where does the chemistry happen? Right where the leaving group is. Is this nitrogen connected to where the leaving group is? No. So for that nitrogen to react to that position must have become reactive. For it to be reactive, there has to be a different functional group there. You want to know what that functional group is? Triple bond. Okay. So we get two interesting reactions coming out of these. Under one case, you have to use a strong nucleophile or base and a deactivated ring. The next case, you need a strong nucleophile or base and a mildly activated ring. Okay. What's happening in these is known as NAS, or nucleophilic aromatic substitution. I know we're done. Okay. Your ring must be electron poor. We showed the resonance effect, so that's why we need the withdrawing group. We need that good leaving group, that's our halogen. Okay. And we have to have the orthopara substitution. Why? Ties back to the resonance argument. Okay. The withdrawing group is establishing that leaving group ability. Okay. So why does the reaction work in one case, not the other? Resonance. We'll come back and look at those maybe. Okay. In some cases, we went through and tried to tweak it and adjust to other things. What do you notice as a condition of differences here? Why is one case working but not the other?
Heat?
A lot of heat. Okay. 350 degrees Celsius is not exactly cool. Okay. The last one happens kind of straightforward. This is the odd result that I wanted to talk about. Okay. You end up forming two products. This chemistry occurs because you form that goofy little structure on the far right. When I said a triple bond, I was serious. Okay. This reaction is so bizarre and interesting, the ACS loves to at least throw one question on it. Okay, so we'll come back and start Wednesday with the benzyne and kind of whip through those. But then ideally, we're just doing kind of review topic stuff.